Adams of FrontierSI and Alla Metlenko of Geoscience Australia, as well as Jessica, Caitlin and Alla. Mike Peters of Geoscience Australia will be available to answer any questions that you might have. The format of today's webinar will be a 1-hour presentation followed by 15 minutes of Q&A, and we invite you to post any questions you have in the chat window at any time during the presentation. During the webinar, we would ask you to keep your video and microphones off, and as well as any questions on the presentation, if you do have any technical issues, could you please post these into the chat window and we will attempt to address these as soon as possible. And so with that, I'd like to hand over now to Jessica. Welcome, Jessica, and could you please start sharing your screen? Thanks. Hi, Jess. I'm just checking. Are you unmuted? Because we can't hear anything.
Hi, this is Caitlin's computer. We're just trying to work out which audio link that we're on, sorry.
Well, we can hear you fine, Caitlin, so whatever one you're using.
All right, we'll go through my computer then.
Okay, sorry. So to outline the webinar, we'll do a bit of background on the Copernicus Australia Regional Data Hub, followed by an overview. What's happening now? An overview of the Sentinel's data applications and case studies. And then we'll look at downloading data through the Copernicus Australasia Regional Data Hub and the different methods to do this, followed by 15 minutes of questions. So I'll just mention that Earth Observation Australia will send out some supporting material and how-to guides to the participants of the webinar in a follow-up email after this. And now I'd like to hand over to Alla to give us background into the Copernicus Australasia Regional Data Hub. And Alla, if you let me know when you want me to move slides, I can do that for you.
Alla, I'm going to unmute you.
Unmute now. Unmute now. Unmute now. Unmute now. Unmute now.
Okay, there seems to be a bit of a problem with the audio. Jessica, we're still seeing your screen, but we can't really hear anything coming from either yourself or Caitlin.
We're handing over to Alla to present the next slides, but we'll still run the slides from our computer here.
Oh, cool, thanks.
Hello? Hi, Alla. You'll need to speak to the slides that Jess has got on the screen.
Can you hear me? Is that, if that's Alla, all we're getting is repetition. I'm not hearing you properly, Alla.
Hi, this is Jess and Caitlin. I think we've sorted out our audio system now. Can people hear us okay again? Great. Thanks, chat. So our intention was for Ella to present this section, but Ella, would you like to try with your audio again, Ella, to see if it's working? We currently can't hear you. Ella, are you there? Given we can't get Ella's audio to work properly, we're going to have Jess present these parts of the slides.
Okay, so background into the Copernicus Australasia Regional Data Hub. So why did it come about? Well, Australia relies very heavily on Earth observation data, but we don't actually have any of our own satellites. And in 2014, the Copernicus program data was going to become free and open. So how did we do this? So the Copernicus program offers a whole lot of data, 2,500 terabytes in the last 3.5 years. And the problem was getting this big data to our region, given the big distance from Europe and the huge volume of data. So the Copernicus Australasia Regional Data Hub, or the Hub as it's known for short, is the regional data repository providing fast, free, open, trusted and reliable access to Sentinel satellite data for users in Australasia, Southeast Asia, the South Pacific and Australia's Antarctic territory. Okay, so the partners and users that are part of the Hub, there's a number of consortium partners, including Geoscience Australia, the Queensland Department of Environment and Science, the New South Wales Office of Environment and Heritage, the Western Australian Land Information Authority, and CSIRO, as well as New Zealand's SARA. And then it's delivered in partnership with the National Computational Infrastructure, known as the NCI, which operate the Master Data Repository, as well as Australia's Academic and Research Network. And the supporting partners in this are the European Commission, the European Space Agency, the European Environment Agency, and the European Organisation for the Exploitation of Meteorological Satellites. So the primary users of the hub at the moment are the partner agencies and some large government organisations in the scientific research community. And the hub is looking to expand its user base to include industry, academia, and non-government sectors across the region. So this image shows the region covered by the Copernicus Australasia Data Hub. So the hub syncs and provides access to data over that region shown in purple for Sentinel-1 and 2, and globally for Sentinel-3 and 5. 5P data will be synced soon, and that will be global as well. So this table shows the data that's currently synced by the hub. Sentinel-1 data is available from 2014 to present, and this is all-weather day-night radar. Sentinel-2 is from 2015 to present, and that's high-resolution multispectral imagery. Sentinel-3 is from 2016 to present, and that's high-accuracy optical radar and altimetry data. And Sentinel-5P will soon be added to the data hub, and this is a precursor to Sentinel-5. Okay, so moving on to a bit of an overview into the Sentinel, the data applications, and a couple of case studies. So the Copernicus program is developing a new family of next-generation Earth observation missions called Sentinels. And this slide shows an example of polar orbiting satellite on the right, and specific images of Sentinel-1, 2, and 3 on the left. So the goal of Copernicus is to replace the older Earth observation missions, which are reaching retirement, to ensure continuity of data so that there are no gaps in ongoing studies. And currently there are 3 complete 2-satellite constellations in orbit, plus an additional single satellite, which is Sentinel-5P. So now we'll give a brief overview of each of the Sentinels, an example of the data produced through each Sentinel, and some example applications. And if you would like more information on the Sentinels, you can find this on the European Space Agency's Sentinel Online website.
I'm just watching a webinar thing. Yep.
So Sentinel-1 is a synthetic aperture radar, or SARA mission. It operates in the microwave range, which penetrates cloud and isn't affected by the amount of sunlight. So the key here is that it can operate in all weather and all day and night. And Sentinel-1 satellites carry single C-band SAR instruments. And the 2 Sentinel-1 satellites in orbit provide high reliability and a short revisit time of 6 days. This slide displays the Sentinel-1 data products that are synced by the Australasian Hub, with the red text denoting the name as it appears in the Sentinel Australia Regional Access Portal, or SARA, which we'll discuss later. So you've got the processing level along the left and the mode along the top. So down the bottom here, we've got the raw level 0 products, and these are unprocessed and mainly useful for scientists who are testing SAR data processing. Then the level 1 products, these have undergone some processing to account for the orbit of the satellite and have been georeferenced. And the difference between single look complex and ground range detected data is that SLC captures the amplitude and phase information of the backscattered microwaves, with phase information useful in interferometric SAR applications, which we'll look at a bit later. And GRD only captures the amplitude information, which is the strength of the polarized backscatter. And then up the top, you've got the level 2 products, which have undergone the largest amount of processing and are ready for analysis. These products are only available for the hub for ocean data, but you can produce useful level 2 SAR products from ground range detected data using certain software packages. This slide shows an example of Sentinel-1 data products. So we've got an auto-rectified vertically polarized data set on the left and an RGB composite of different polarizations on the right. This is a demonstration of how different polarization measurements can be combined to make a 3-color image, which highlights various features in the landscape. So in this image, the buildings stand out very clearly due to their strong vertical backscatter intensity, which has been encoded as green in the 3-color image. SARA applications can be split into applications of backscatter products and applications of INSAR products. So backscatter is a measure of the strength of the polarized backscatter, and INSAR refers to interferometric SAR, which is using 2 or more images to look at change via differences in the phase of the wave. It can potentially measure millimeter scale changes over days to years. So this video is a global example of a backscatter oceanography application. And usually the ocean is very calm and appears as uniform intensity in the radar backscatter measurements. So anything unusual, like these oil spills, show up very clearly, which demonstrates that Sentinel-1 is suited to this kind of detection. So some other interesting INSAR applications include things like fracking, underground tunnelling for metros, and tailings dams for mines. Okay, so this is an INSAR application showing time series analysis of surface deformation. The shapes in the left image are sections of an underground mine, and in both of the views we are seeing the deformation on the surface above the mine in meters over a 3-year period. And this graph plots that same mine site deformation as measured by a geodetic grade GPS core station, so very high accuracy, and as measured by INSAR. So you can see the blue, green and red is the GPS information, and the light blue and orange is the INSAR. And you can see that the INSAR results are as good as the GPS, they match up very well. And in addition, when the GPS had a power outage, which you can see in the gap in the GPS information to the right of the graph, the INSAR was actually able to fill this gap. So it's a very useful technology. This is an Australian case study using Sentinel-1 radar data for surface deformation monitoring. So Geoscience Australia monitors, analyses and reports on the occurrence of significant earthquakes in Australia. And this is done using seismometers, which provide rapid information on the magnitude and location of an earthquake. But the uncertainties on the location are large due to the sparsity of the seismic monitoring network. So INSAR fills this gap by mapping the spatial patterns of ground surface movement that have occurred in the time between the acquisition of 2 synthetic aperture radar images, and it allows field teams to target their efforts. So for this image, on the 16th of September 2018, a 5.7 magnitude earthquake occurred in Western Australia. And the seismic data showed that it may have produced surface deformation. However, based only on the data with large location uncertainty, it was difficult to locate where or even if surface deformation had occurred. So GA used Sentinel-1 data to produce this interferogram, where the epicenter is the star, the dotted black line is the about 5 kilometre long fault line, and there's about 28 centimetres of surface displacement on the eastern side and about 6 centimetres on the western side. So that covers Sentinel-1 in as much detail as we're going to look at today. Moving on to Sentinel-2. So Sentinel-2 is a multispectral optical imaging mission sampling 13 spectral bands. It has high revisit frequency of 5 days at the equator. And multispectral instruments produce the typical satellite images that we think of. So the different spectral bands are combined to produce a photograph of the Earth. And Sentinel-2 currently provides the highest resolution and most frequent revisit time of freely available optical satellite data. This slide shows the Sentinel-2 data products synced by the Australasian Hub. So there's a level 1 top of atmosphere reflectance product and a level 2 bottom of atmosphere reflectance product. The level 2 product has only been produced since December 2018. So for level 2 data before this time, users can download the level 1C product and then use a tool like Send2Core to process it to level 2A. Here is an example of Sentinel-2 data. So the image on the left is the top of atmosphere image, which you can see is hazy when you compare it to the bottom of atmosphere image on the right, which has had the atmospheric correction applied and is much clearer. These are some applications of Sentinel-2 data for land monitoring, emergency management and security. The image here shows a global example of fire monitoring in Greece. So vegetation appears red in this false colour image and the burn scars appear black. However, users need to be aware that water also appears black. And you can see the large burnt area to the north of the image. So this could be used to generate things like fire extent information. This image shows an Australian example in the Great Barrier Reef for the monitoring of coral bleaching. Bleaching happens when algae living in the coral's tissues, which capture the sun's energy and are essential to coral survival, are expelled due to high water temperatures. So you can see that the coral has turned white in the image from February, and this is bleaching. So Sentinel-2's frequent revisits and high resolution make capturing events like these from space possible. This one is an Australian Sentinel-2 case study. So the Australian red meat and livestock industry makes up a big chunk of our gross domestic product, and there are productivity gains to be made within the industry. So SIBO Labs is an agricultural data analytics company based in Queensland that is working in this area. They use pre-processed Sentinel-2 imagery provided by Digital Earth Australia with on-ground data and their own machine learning techniques to look at pasture biomass estimation, land condition monitoring, and land management tools for the livestock industry. Being able to access the pre-processed Sentinel-2 surface reflectance products in near real time has enabled SIBO Labs to focus on value-added products rather than spend their time processing data to analysis ready. So the tools they are developing increase productivity for producers through improved understanding of their land condition and pasture health. So that covers Sentinel-2, and now we'll look at Sentinel-3. So the objective of Sentinel-3 is to measure sea surface topography, sea and land surface temperature, and ocean and land surface colour. So to do this, it carries 4 main instruments: the ocean and land colour instrument, the sea and land surface temperature radiometer, the synthetic aperture radar altimeter, and a microwave radiometer. The 2 satellites enable a short revisit time of less than 2 days for ALTI and less than 1 day for SLSTR at the equator. This slide shows the Sentinel-3 data products synced by the Australasian Hub, and again the red text denotes the name as it appears in the SARA portal, which we'll look at shortly. So here the processing level is again displayed on the left, and then along the top we've got the instrument or product. So ALSI provides level 1 top of atmosphere radiant data, and then it provides level 2 land and atmosphere data, including things like a global vegetation index, terrestrial chlorophyll index, and water vapor data, as well as level 2 ocean and atmosphere data, including algal pigment concentration, total suspended matter concentration, and aerosol load over water. Synergy is not an instrument, it's actually a synergy of the ALSI and the SLSCR products, and it includes surface reflectances, aerosol load over land, and vegetation-like products, providing a maximum normalized difference vegetation index, or NDVI. Then you've got SLSTR, which provides level 1 brightness temperatures and top of atmosphere radiances, and level 2 sea surface temperature and land surface temperature. And finally, the topography mission provides level 2 land data, including surface backscatter, surface height, altimeter range, snow density and depth, and level 2 marine data, including sea surface backscatter, sea surface height, significant wave height, ocean depth, tide heights, and so on. Here are some examples of Sentinel-3 data products. So first we've got global sea surface temperature from the sea and land surface temperature radiometer in degrees Celsius from June 2017. And you can see, unsurprisingly, that temperatures are highest around the equator. This one is global algal pigment concentration from the ocean and land colour instrument in milligrams per metre cubed from June 2017. And here you can see that the concentrations are highest in the north of the northern hemisphere. So there are different applications for each of the Sentinel-3 instrument products. And this image here is an example of an extreme heat wave in Europe from the sea and land surface temperature radiometer. The animation of 2 images shows the land surface temperature from the 25th of July 2019 compared to data recorded during the previous heat wave on the 26th of June 2019. So here clouds are visible as white, and the light blue represents snow-covered areas. This global animation shows ocean and land colour instrument terrestrial chlorophyll index over a year. The OTCI is estimated based on the chlorophyll content in terrestrial vegetation and aims at monitoring vegetation condition and health. And this is just an example of the Sentinel-3 ocean and land colour instrument capturing Cyclone Debbie as it struck Eastern Australia on the 27th of March 2017. So that covers Sentinel-3, and now we're going to have a little look at Sentinel-5P. So Sentinel-5P is a precursor mission to Sentinel-5, and the objective is to perform atmospheric measurements. It has 1 satellite carrying the tropospheric monitoring instrument, and the Sentinel-5P data will be available soon on the Copernicus Australasia Regional Data Hub. So Sentinel-5P helps address environmental concerns such as the quality of the air at the Earth's surface, which is impacted by aerosols, ozone and other reactive gases such as nitrogen dioxide, affecting human health and life expectancy and the health of ecosystems. So this GIF here shows total ozone and the ozone hole over Antarctica in 2018. here we have an example of a Sentinel-5 application, and this shows carbon monoxide from the Amazon fires. So the image shows the difference in carbon monoxide in the air between July 2019 and August 2019 over the Amazon. This pollutant is often associated with traffic, but here we see the increase in atmospheric concentrations following the fires. So once in the air, it can cause problems for humans by reducing the amount of oxygen that can be transported in the bloodstream. And this final example here is an Australian example of Greenpeace using Sentinel-5P data to map nitrogen dioxide levels against coal-fired power plants in Australia. Okay, so now we're going to move on to working with the Copernicus Australasia Regional Data Hub and how to actually access the data via the different options that are available to users. So there are multiple ways to access data from the hub. There is the Sentinel Australasia Regional Access Map-based GUI known as SARA. There's the SARA Python API, which is for more advanced users. There's the NCI's thread server, and also directly through the NCI's file system for registered users of the NCI. So the SARA map interface and the API are the recommended access paths, and we'll now run through an example of downloading data with both methods, as well as using the thread server. So an overview of the process using the SARA GUI is first to register, then you log in, explore the data, and you can download a single image at a time. So from the Copernicus Australasia Regional Data Hub website homepage at this link here, you can then click the Regional Data Access tab, followed by the Sentinel Australasia Regional Access Interface link. Otherwise, you can access the SARA homepage directly from that link shown there. And anyone can explore data on SARA, but users must register to download data. So if you click the register button at the top right, registration is free and it helps the hub to understand the number and variety of users. So just complete the registration details and you click register, noting that if you're going to use the SARA Python API for bulk download, it's best to use a simple password without any special characters like exclamations or $signs to ensure the scripts work smoothly. So once you've clicked register, you should then receive an email from the NCI titled SARA activation code, and if you click the link in this email to validate your SARA account. So if we go back to the login screen, you just use the email address and password used to register for SARA and click sign in. And the homepage now displays My Cart and Profile buttons instead of Login and Register at the top right. If we go back to the homepage, so the SARA homepage does provide a search bar, but it isn't the best place from which to search. So it is useful for semantic search over relatively small places. For example, if you enter Canberra, April 2019, Sentinel-2, it will return the data shown here. So there's a map view of the data available for that search and a list view as well. However, to search more accurately using more detailed search criteria, click the Explore button. So it's very useful at this point to know a bit about the data that you want to download. And you can search on any combination of criteria or no criteria, but the more criteria provided, the more targeted the results will be to your requirements. So the search criteria applicable to each mission are shown in this table. So along the left, we've got the different criteria available, and along the top, we've got each of the Sentinel missions. And for Sentinel-1, the cloud cover criteria is not applicable. The Sentinel-2 sensor mode, orbit direction and polarization are not applicable. And for Sentinel-3, only instrument type, product name and area of interest are applicable. So today we're going to download a Sentinel-1 SARA ground range detected interferometric wide swath standard dual polarization image from the 31st of August 2019. So to limit the acquisition period, we're going to use the calendar to select the begin date as the 1st of August 2019 and the end date as the 3rd of September 2019. And to clear a selected date, you can click the X to the right of the relevant box. So to specify the Sentinel mission, we're going to select S1 from the collection drop-down box for Sentinel-1. For the instrument and product name criteria, I've got a table that shows you a bit more detail. So this one shows the Sentinel instruments that are available for each mission. And the table on the right shows detail of the Sentinel product names and their descriptions. So to specify the Sentinel instrument, we select SARA in the instrument drop-down box. And you can see that if a collection has already been selected in the above box, then the instruments available in the list are reduced to those applicable to that collection. To specify the Sentinel product, we select GRD from the product drop-down box. Again, you can see that if collection has already been selected, the products are reduced to those applicable to that collection. For the sensor mode, orbit direction and polarization criteria, these tables show what's available. So for sensor mode, you've got extra wide swath, interferometric wide swath, strip map or wave. For orbit direction, you've got ascending or descending, so from south to north or north to south. And from polarization, you can either have single or dual polarization, with the first letter representing the transmitted polarization and the second letter representing the received polarization, with H for horizontal and V for vertical. So to specify the sensor mode of interest, we're going to select IW in the sensor mode drop-down box. And if S2 or S3 had been selected as the collection, the sensor mode would be applicable, so there would be no modes available in that list. To specify the orbit direction, you'd use the orbit direction drop-down box to select ascending or descending, but we're going to leave this blank as both directions are relevant here. And if S2 or S3 had been selected as the collection, then orbit direction wouldn't appear at all as it's not applicable. So you would specify the polarization using the polarization drop-down box with VV plus VH is what we're interested in today. But there's actually a bug with the dual polarization options in the SARA GUI at the moment due to a metadata issue, which returns a no result warning despite results actually existing. So the current workaround is to just leave this option blank. And again, if S2 or S3 had been selected as the collection, the polarization wouldn't appear as it wouldn't be applicable. As we've selected S1, cloud cover isn't applicable and the option doesn't appear. However, to specify the maximum cloud cover percentage allowable for the data, the cloud cover scroll text box would be used to select or type a whole number between 0 for no cloud cover allowed and 100 for total cloud cover allowed. So to specify the area of interest, you click the Draw an Area of Interest button. Then you can zoom in on the map using your mouse wheel or the plus or minus zoom buttons. And we're going to zoom into Lake Eyre in South Australia. You simply click on the map to draw a rough boundary of the area of interest, with each click creating a new vertex and then double click to finish. And when all your desired criteria have been provided, you can click the search button. If no results exist, a red warning would appear at the top of the screen and there would be nothing in the map or the list. However, if results do exist, the map view will display these spatially, as you can see in pink here. And then scrolling down will reveal a list of data sets matching the search criteria. So there you can see the options available on the map. and a list of data sets. And we're going to click on the details button for the 31st of August 2017 811 results to see further details and properties. So you get a map showing the location of your data, a quick look of the image, and then all the properties for that data set. So then to download, you'll click the download icon on the dataset details page and simply start downloading, as you can see there in the bottom left. You can also add multiple items to your cart to download, but this becomes complicated as it actually downloads a meta4 file, which then requires additional software and command line to access. So we recommend using the SARA GUI to download a single image at a time. And if you wish to download more than a few images, the SARA API should be used for bulk download. Okay, so I'm now going to hand over to Caitlin to talk us through download with the API.
Great, thanks, Jess. Hi, everybody. So in this section, we'll be talking about how to perform the bulk download using the SARA Python application programming interface, which I'll refer to as the SARA API. So to use the API, you'll need a basic understanding of Python and how to run Python from your computer's terminal application. You'll also need the email and password that you use to sign up to SARA, like Jess showed in the previous section, a terminal application such as Anaconda Prompt for Windows or Terminal for Mac and Linux, an installation of Python. We recommend that you do this through Anaconda, an installation of the ggal Python package, and a program to unzip files such as 7-zip. So today we're going to demonstrate how to perform the download on a Windows setup. So the download is done through a number of existing Python scripts that can be used with the SARA API. So we're going to download these scripts from the Copernicus Australasia Regional Data Hub Bitbucket page, which you can see on this website. So start by going to the download and then clicking the most recent file. Once the download is finished, you'll need to move that download to where you would like to keep the scripts. So here I'm going to copy the file and then paste it into a folder I've created in the documents called AusCop Hub. And this is where we're going to be working throughout the webinar. So to get access to the scripts, you'll need to unzip these files. So there are 2 levels of zip that you'll need to do. So here I'm doing the first one with 7-zip. This makes a dist folder. You'll then need to enter that dist folder and perform a second extraction. So now we're left with the AusCop Hub folder, and in here, this will contain the necessary files. So we'll now cover how to actually install the scripts. To do this, you'll need to copy the location that the scripts are stored, because we'll be using this in the terminal application. So I'm now going to switch to Anaconda Prompt, and you'll need to start by moving to the folder the files are in by using CD and then the path name. So once I've moved to that location, we'll be able to actually interact with the script directly. And we can do that first. The first thing we'll need to do is run the install. And that's done through the command Python, then setup.py, and then install. So running this command will actually install the script, and it'll create a new build folder in that original file directory. So you can see that here. If we enter the build folder, there should be a scripts file. The number here is the version of Python that you use to install the script. So entering this file, we can see all of the SARA scripts. We'll be looking at the AusCopHub_search_SARA.py script, which will allow us to make other scripts to automate bulk downloading. So to use it, we're going to copy it into the file, the folder path that we want to run it from. In this case, I'm going to put that in the AusCop Hub folder higher up. So we're now going to cover how to run this script to automate the bulk download process. So I'm going to start by copying the file location, because again, I'm going to need to get to this folder from the terminal. So we're going to start by, again, using the change directory command cd to move to the new file path. So here it goes, cd, then the file path that I copied, and I've now moved there. So to investigate a little bit more about how the script works, we're going to start by interacting with it through, again, you start with Python, then the name of the script, so this is the _search SARA, then -- help. So this lists all the command line options that are available for this script. There are quite a few of them, so I'm about to pull up a slide with a little bit more detail about each of them. So the important thing is that there's lots of different ones, but they fall into two general sort of categories. So they either relate to constructing the query for the download or for specifying the form of the output. So for this webinar, we're now going to cover how to use the query param argument and the curl script argument to download our data. So there are a number of ways to specify a data query, which are passed to the script using this -q command. The structure is -q, then in quotes, name equals value. So there's the names here and examples of the sort of constraint to pass to that parameter. So again, these parameters fall into a couple of categories. So there's the location-based ones, the dates, and then any instrument specifications. You can see these are sort of similar to how the SARA GUI page works as well. And your instruments will change depending on what data you want to download. So in this example, while there are a number of ways to specify how you want to download the data, we're going to focus on using the search SARA Python script to make a curl script for our query. And then that's what will automate the bulk download process. So this is done with the curl script and curl options, command line options. So here, sorry about that, the curl script is the name of the file where we'll be storing it, and the curl options will be used to specify the username and password, and that's what's actually authenticating the download. So I'm now going to take you through building this sort of call to generate an automated download. So the start is to call the script. So we've got Python, then the _hub _SARA.py, and then we can start passing our query. So I'm going to start with the location. So here I use -q, and then quotes. I'm going to use the name parameter for that sort of semantic search. And I'm going to type in Canberra, Australia. So following this, I want to specify the date. So I can do this with another -q parameter, which is start date. I'm going to pick the 20th of August, 2018. And then I'm going to specify the completion date parameter, which I'm going to set as 6 days later. Because I'm just constructing a simple query, I haven't specified which sentinel I want to look at. So the script is just going to return data for all of them in this 6-day window. So now that I have the location and the date, I'll need to tell the script how to deal with the curl script section. So I start by using the curl script command to pass the name of where I want to save the curl script. In this case, I'm going to name it after the location and my start and end date. But you can call these scripts whatever is most useful for you in order to, track what they're actually downloading. So the thing that's important here is on Windows to finish that file name with the .bat extension, and this tells Windows that it can run that as a curl script. So finally, I need to pass the username and email to authenticate it. So this is done through the curl options command line. So in quotes, you have -u and then your email and password. So if you were doing this for real, you provide your actual email and password. I'm using a dummy email and password for confidential reasons. So we're not actually going to download any data in this format today. So now that I've passed all the necessary information and hit enter, the command is going to run to generate the script that will download the data for us. This can take a little bit of time, and once the script is finished running, you'll see a return of your command prompt. So that's that there. So now that we've built the script, we should be able to see that Canberra date.bat file in our folder, and we can see that it's there. So now we're going to go back to the terminal and run this using / and then the name of the bat file. So when I press enter here, you'll see it run a large number of commands. At the moment, it's not actually performing a data download because the email and password aren't a real email and password. But you should see a similar sort of output if you've provided your email and password. So as it downloads, you should have files appear in the same folder that you're running the download from. And it's important to note that your email and password will actually be displayed on the screen as the download progresses, so you may want to keep this in mind when running these scripts. We'd also recommend that once you've finished running them and you no longer need this, to delete it because it will contain explicitly your email and password. So the data will appear in this folder and you should now be able to use it. Depending on the product that you download, the data may need some additional processing to be suitable for applications. So I'm going to hand back over to Jess now to finish up.
Thanks, Caitlin. So now we're going to have a quick look at, if we can skip past that slide. Okay, the threads, downloading data from the thread server. So in overview, simply access the server, navigate the folder structure and click to download your data. So from the Copernicus Australasia Regional Data Hub website homepage, at this web address here, you click the Regional Data Access tab and then the thread server link. Or you can access the thread server directly at that link there. So anyone can explore and download data from the thread server and registration is not required. The folder structure and file naming of data on threads is the same as for the data on the NCI, with the file naming replicated from Europe. So we are going to download the same data set as we downloaded from the SARA GUI. But this slide shows a bit about the folder structure. So for Sentinel-1, you've got the Sentinel collection, the instrument, the product name, the year, and the month, followed by the location or 5-degree latitude bell. So an example of that is Copernicus, Sentinel-1, CSAR, SLC, 2014, 10 for October, and then the 5-degree latitude cell location. And for information about the file naming details, you can follow the link here. For Sentinel-2, the folder structure is very similar as for Sentinel-1, with the main difference being that product level is used instead of product name. So that's the L1C product level. And again, that link shows the file naming details. The Sentinel-3, the folder structure is similar again with Copernicus, the Sentinel collection, an instrument folder, product name, year, month, and then day at the end instead of 5-degree location. And so there's an example and the file naming details for each. We're going to download the same data set as we did from the GUI, so click the Sentinel-1 folder, the GRD folder, the 2019, and then 08 for August. And then you need to know the latitude coordinate location of the data. So we're looking for 25 south 135 east, 30 south 140 east. So there's that one there. And once here, you need to understand the file naming system described at the links shown previously. But if we scroll to the bottom and click the PNG and then the HTTP server link, we can view a quick look, which is downloaded, and you can see that it is the same image that we downloaded from the GUI. And then if we go back and click the zip file, and then the HTTP server link, that link will actually download the data the same as we did from the GUI, and you can see that in the bottom left there. So that's it for the thread server. It's pretty straightforward, but you do have to know about the file naming. And then quickly an overview of the NCI file system. So registered NCI users with the relevant project permissions